So firstly, I will explain you what basically an operation amplifier means, and then we will deal with how operation amplifier is used in two modes, which is inverting amplifier and non-inverting amplifier. That is the first part, and then we will move to the second part, wherein you will be taught how to use this operation amplifier as an integrator and a differentiator. So let us get started. So firstly, operation amplifier is not a new component. It is basically made up of a few handful of transistors and few supporting passive components, which are connected in a particular configuration. So ultimately, to give us a few unique properties, so such as very high gain. So an operation amplifier has very high gain and high input impedance, and the main property that distinguishes it from a general transistor is that the input, the inputs here is the type of input it takes is a differential input, meaning that it has two inputs basically. So one is a positive terminal and the negative terminal, and the difference between these two inputs are processed, and they are taken through a particular set of functions, and ultimately it gives us a single ended input output. So the output will be one, but then the inputs will be two, right? So firstly, now an operation, like I said, it is made up of few transistors which are connected in a certain fashion. So you can say that it has a few, three, four stages basically. An operation amplifier has four stages. So the first stage mainly deals with the differential stage, wherein, like I said, we'll use two transistors. Each one will take two inputs, and the outputs generated, the difference of these outputs are processed and they are taken to the next stage. And again, that output is again sent through a voltage amplifier, wherein since generally the output, since it is a differential output, it is a weak signal. So in order to amplify it, we use a voltage shifter or a voltage amplifier, and then it is taken through two more stages, which is a current amplifier and also a current mirror. So I do not want to go deep into this particular stages and all, because it's a lab session. So just remember that how an operation amplifier is different from a transistor, and how it is made up of through these different stages, right? So an operation amplifier, which was generally was actually introduced somewhere in I mean, early 40s, 1940s, but then it has been available in IC form since 1960s. So right now in labs we will use operation op amps as IC using IC741, which is the standard operational amplifier. And if you can see here, this is the uh, internal structure of 741 IC, and this is the basic symbol of the operation amplifier. So you can see that it has two inputs, non-inverting input and inverting input. So the non-inverting input is the positive terminal, inverting input is the negative terminal, and it is powered through the supply voltage, positive and negative, and then it is taken to the output. Yes. So next, so this is the basic introduction to what we can also call an operation amplifier as an op amp. Then, so like every electronic, so in electronics, what happens is that we whenever we you know invent a component or a device, so we expect it to function in a certain way, and we generally introduce a theoretical concept called ideal component. So that is the same case with the operation amplifier. So we expect ideal operation amplifier to perform in a certain way, and to exhibit certain characteristics, so that we can compare this ideal operation amplifier with the one which we have manufactured, to see how close the characteristics are, how close we can construct it with respect to the ideal theoretical concept. So, so for an ideal operational amplifier, it must have infinite open loop gain. It must have infinite input impedance. So, in order to have high immunity towards the noise currents generated through noise at the inputs, and have high output impedance, and also it must cater to all the frequencies present. I mean, infinite bandwidth, and also whenever we connect no input, we connect these input terminals to ground, the output must be zero. That is the meaning of zero of offset voltage. So we expect an ideal operation amplifier to perform in this manner, right? So now let us get into the first part. So before this, So before before getting to how op-amp is used as an inverting amplifier, so we have to understand that since I said it has a very large gain and very high input impedance, so this component is highly unstable and highly uncontrollable. So whenever we use this component, we expect some output to be generated in a desirable manner, right? So like if we operate a sinusoidal signal, so we expect some output. So now if it is unstable, so we cannot observe the right signal at the right time, and we will not be able to control if we are not able to control the component, so we cannot rely on it. So that led to the proposition of a concept called as feedback. So now we use feedback here in order to make it stable, to control the gain, so that we can obtain the desirable output with respect to respectively. So feedback is nothing but, in electronics, feedback is nothing but we give a part of output signal back to the input using a passive component such as a resistor. So here we are using this feedback resistor and we are giving it back to the input. So since here in this particular operation in inverting and non-inverting amplifiers, what we do is we are controlling the gain and we are making it stable, and we are making it stable. So now in order to do that, we have to connect the feedback to the negative terminal. So here we have connected the feedback to the negative terminal of this device, so that ultimately it can give us a stable and controllable gain. So gain is nothing but the output, the rate of, so the improvement in the amplification, right? So how many times the output has been multiplied with respect to input. So which is V out by V input. So since so now since we've connected this output, so now this operational amplifier acts in two modes, like I said. So if we connect the input voltage to the negative terminal of the operational amplifier, we say it is in the inverting mode. And if we connect the input voltage to positive terminal of the amplifier, we say it is in non-inverting mode. So here, since it is an inverting amplifier, we say we connect the negative terminal of the operational amplifier to input voltage, right? So now the connections are clear. So now since we have connected the input voltage to negative terminal, and we've used a negative feedback, since it is connected to a negative terminal, we say it is a negative feedback system. Now in order to obtain the relation between output voltage and input voltage, so we take a certain concept which is called as virtual short. So here you see, now like I said, it has an operational amplifier has very high input impedance, right? So now if we connect a voltage in here, and now this current is flowing in this branch. So now when it reaches this V2 terminal, X terminal, so the current does not flow towards the inverting input here, because the impedance is very high, that no current flows through this branch. So you can say that the feedback current flowing from V2 to V out is equal to the input current flowing from V into X. So using this relation, we can obtain the final equation which equates which relates the output voltage with input voltage. So using this relation, we say that In is equal to If, right? So now the current equation, which is, the current value In, we can say in terms of input voltage as Vin minus this terminal, the voltage at this node, which is V2. Vin minus V2 by Rin, right? Resistance. And then here the current flowing through this part is from here to here. So V2 minus output voltage V out by feedback resistance RF. Yes. So after this, we like I said, there is an important concept called as virtual short, which ties up the entire equation here. So here we say, since it has very high gain, you can say that the voltage at this terminal V2 and voltage at the positive terminal V1 are equal. So you can say simply that V2 and V1 are shorted here, so that these two voltage, we can theoretically assume that these two are shorted which we call as virtual short. They are not actually shorted, but then the difference between these two terminals, the voltage difference between these two terminals will be approximately zero. So we will use so this concept has few shortcomings. So that that is the reason why we will use it when we connect only this it in a negative feedback fashion. So whenever we connect a negative feedback, we use this concept. Yes. So next, since we are using this concept, so here the positive terminal is connected to ground, and so this V1 equals V2, which is 0. So that is the reason why here we can call it as a virtual ground concept. So now the V2 here is 0. So when we substitute this value here, and we can get the direct relation between the output voltage and input voltage as V out is minus RF by Rn into Vn. So this is the output voltage relation for an inverting amplifier. If you observe carefully, the output voltage here is in 180 degrees phase, out of phase with respect to the input voltage because of this negative sign. So whenever you are plotting this in the VLab, you have to observe a diminishing curve, a linear curve, which is a straight line, which is decreasing. So this is the inverting amplifier. The next is the non-inverting amplifier. Here there is no change except for the fact that the input voltage is connected to the positive terminal of the device, and the negative the feedback will be negative, right? The feedback will be RF and it will be connected to the negative terminal, and the input resistance will be connected to the ground. And the only change is that we connect the input voltage to the positive terminal of this device. So now, like we've equated this 0 volt voltage here, we will also equate this input voltage to this V1. So if you observe this branch, which shows the IF current and the IF from V out to R2, since here no current flows through this part, so we can see that this is a straight one branch, single branch curve, single branch, and you say, and this voltage here is the voltage across this R2. So this V1 here can be considered as a voltage across this resistor, and so we apply voltage divider network here, and we can obtain the equation for V1 and V out as like this. So V1 is R2 by R2 plus RF into V out, and then we can finally obtain this relation between the V out and V in as 1 plus RF by R2. So if you observe here, for a non-inverting amplifier, the relation between output and input, the phase difference is 0. So you can observe a increasing, whenever we plot the VI characteristics, you can observe an increasing straight line, right? So this is the first part. So let me show you the, so should I show them the virtual lab, how to connect and all?
Yeah, sure.
Yes, yes.
You can show these two and then next two.
Yes, sir.
Yeah.
So, sir, can you see the VLab, sir, website?
Yeah, it's visible.
Yes, yes.
Yes, yes.
So first, let's go to the inverting terminal. So what you have to do is here, the input voltage swing here, which is available for you guys, is from minus 15 to 15 volts. So firstly, you have to connect it in the fashion shown here. So make the connections as per the circuit diagram, and then vary the input voltage from minus 15 to plus 15. Increase the voltage for every like 2 volts, increase 2 volts, and generate the tabular column. First check the connections, it is the right connection. Now set it to some minus 15 volts and set the, so vary the R1, the resistance of the first, R1, you can vary it from 1 to 50 kilo ohms, and vary RF from 2 to 100 kilo ohms. Yes, so I will set it to some 20. So now the gain will be, so for minus 15 volts, for a resistance of, for a gain of minus 20 by 5, which is minus 4, you have to obtain 60 volt. Yes. Okay. Add it to the table. Yes. Now you can increase it to 13. Add it to the table. 10. Add it to the table. So when you plot it, you have to obtain this negative slope, straight line with negative slope. So this is the simulation for inverting operation amplifier. Then we'll go to non-inverting. You can see the non-inverting amplifier, right? So we have to connect it in similar fashion. Check connection. It is the right connection. and then similarly set. Now I'm getting the input voltage, add it to the table. And plot it. So you have to obtain a straight increasing curve with a positive slope. So yeah. Now Santosh sir will take over here and he will explain you the how to use operational amplifier as integrator and differentiator. Sir?
Yes, I'm present.
Yes.
My screen is visible, right?
Yes, yes.
Okay. Till now, we see that we can use a register at the input side and another register at the feedback side. So we are having a inverting or non-inverting configuration. So let's see what will be the change we'll do. Means I will do a simple, I will add another reactance component like capacitor, or so we'll see what is the output voltage we are changing. Means how this output voltage we're changing. So as we are focusing on this current IN and IF, the feedback current and input current. So here we can see that this IN input current is equals to V in by R in, and this IF current through this capacitor is minus C dV out by dt. So as there is no current flowing through the op-amp due to this virtual ground concept as explained, so this IN becomes IF. So here we can see that V in by Rin is equals to minus C dV out by dt. We right now, if we rearrange this whole equation, this V in by Rin equals to minus C dV out by dt, then we can see that our V out is equals to minus 1 by Rin C integration from 0 to t to V in by dt. Here we can observe that our output voltage V out is directly proportional to the integral of input voltage. This integral of input voltage. That's why we can say that if our capacitor is placed at the feedback side, and then this op-amp circuit can be act as a integrator, because our output is directly proportional to the integration of V in. And this that there is a proportional constant which is equals to minus 1 by Rn into C. This minus is due to our non-inverting configuration because our Bin is connected to input terminal, inverting terminal. So that's why this minus 1, and this minus 1 by Rn into C is our gain, that AB which we are focusing on. Then let's say we are giving an input as a square wave. This Bin is equals to a square wave. Then we know that this square wave is a combination of step inputs. So the output is also going to be a combination of ramps. So with respect to this square wave, we are having a sawtooth as an output by adjusting our time constant, this Rn into C. Because we are having a C and R, so this become our RC network. This RC network, that means it has a time constant. By manipulating this time constant and this fixing this duty cycle, we can also achieve a triangular wave also.
Input, it is shown that the voltage is 0 volt. So in the 0 volt, V out should be, means the value of V out should not change during that interval, sir.
Here you are having a capacitor. That capacitor, with respect to our time constant, that capacitor is going to charge and discharge. So that part is connected. If you are having a 0 volt, let's connect it to the 0 volt, then capacitor doesn't have any frequency. So the capacitor will be open. So that reactance is there. So Xc will become infinity. So that's why it will start charging and discharging. That property is there. So with respect to that only, we are getting a triangular wave. If you are connected with any sine wave, then integration of sine is minus cos. That part you can achieve, or you can focus on, means the output will be minus cosine. But if you are having a because we are connecting B in the inverting terminal, it will become a cosine wave. So next, right now we have just connected a capacitor at the feedback terminal. So what if I'm placing a capacitor at the input terminal? Just I'm interchanging, and in the feedback terminal we are having a resistor. With the same concept, we'll focus on this IN and IF. So and there is no current through this op-amp circuit due to this virtual ground concept. So our V out, this IF current is equals to minus V out by RF, and this IN current is equals to OC dV in by dt. So as this virtual ground concept is there, so we are saying that IN equals to IF. This C dV in by dt is equals to minus V out by RF. Again, by rearranging this equation, we will reach out that V out is equals to minus RF into C into dV in by dt. So here you can see that our V out, this voltage output, is directly proportional to the input voltage's rate of change with respect to time. This rate of change with respect to time. So we are saying this one is a differentiator configuration. This op-amp's configuration, we say it is a differentiator. Similarly, we are having a V in as a V in at the point of inverting terminal. That's why this minus part will be there, and this RF into C is the gain of our differentiator. So what will happen if we give certain inputs to the op-amp, this differentiator circuit? If I give a square wave as an input, then differentiation of the square wave is pi, and triangular waves differentiation is rectangular, and sine waves differentiation is cosine. So like that, it will give a different outputs. So let's see how in the BLF what we are having. Integrator. At first, we are going for integrator. So at the integrator, we see that the capacitor is at the feedback terminal, and the input is given to the inverting terminal through a resistor. So Vin is connected to resistor, then resistor is connected to inverting terminal. This capacitor is connected to inverting terminal. Output, there is a capacitor feedback, so output is connected to capacitor, and non-inverting terminal is grounded. Here we are having a oscilloscope's 2 channel. So one channel is connected to input terminal, another terminal is connected to output. So let's check our circuit. Yes, it's a right connection. Then I fix our input resistance as a 10 kilo ohm and capacitance as a 0.1 microfarad. Then I switch on my circuit. I gave as a square wave as a input. Oscilloscope, I saw the oscilloscope output is the square wave. So oscilloscope, you can see that output is triangular. So let me set as a dual mode. Let me fix my volt for division, so you can give a proper output. We can see. So let's say we set this. Here you can see that it is just with respect to square wave, we are getting a triangular wave because it's the integrator circuit. That's what integrator do. So let's change our square wave to a sine wave. So well move. Okay, here you can see that we are giving input as a sine wave, and there is an output curve is coming out like this. Here with this, there is a DC offset. Okay, this is we should not get any DC offset in the integrator, but this is the BLF has some problem. That's why we are getting a offset. Otherwise, it will come bit higher. Okay, here we can say that here it is having a DC offset. This should not be there. Okay, keep in that mind. Here we are having a sine wave, but the output is plus cosine wave. But in mathematics, we know that integration of sine is minus cosine. This plus due to the input is at the inverting terminal. Okay, this is the integrated part. Let's go for differentiator. In the differentiator, we have the input same same circuit, only we interchange the capacitor and resistor place. So let's connect our input to the capacitor. Capacitor is connected to inverting terminal. Resistor is connected to inverting terminal, and the feedback resistor act as a feedback. Then this non-inverting terminal is grounded. Oscilloscope's one channel is connected to input, another channel is connected to output. Let's check our connection. Yes, it's right. Okay. Then I'm keeping a capacitance of 0.1 microfarad and resistance of, let's say, 10.5 K. Then I'm switching on my circuit. Let's give it a square wave as the input and see the oscilloscope output. Let me set as a dual. Yeah. As shown in the slide, you can see that with respect to whenever there is a change in the square wave, there is a spike. This spike is generating. But if I'm changing my frequency, okay, this spike is not going to change. Okay, I don't know. There is a problem in the VLAB, most probably. So that's why this spike is not changing. Otherwise, it is means in the real life, in the lab, you can directly see that with respect to if I'm changing my frequency, the spike should change. But this VLAB has some error, means some design problem. So that's why this spike is not changing its place. Okay, so let's change my input to sine wave, this sine wave, and oscilloscope output. Let's make it dual. Let me adjust the volts per division. Okay, it's fine. So here you can see that the sine wave has a output of cosine wave, but there is a negative sign. If as here it starts with the minus 90 degrees, so you can say that it is the output of minus cos wave. So this minus is due to this inverting configuration. So you can see that. So in the differentiator, with respect to this square wave, there is a VLAB limitation is there. Okay, and in the integrator, there is a limitation in the output of this sine wave. This offset is there. These two VLAB has a limitation. So you will see. So thank you. This is from our side. If you have any query, you can ask.
Yes, please go ahead with your questions. No questions? Okay, so yeah, so if you don't have any questions, couple of points. We know that next week you have your test week, okay, but because the week 2 weeks after that, Tuesday is the holiday, right? So on 12th you have the Durga Puja holidays, and 19th I think there is some festival, and therefore the institute is holiday, so you don't have classes. So therefore we have to conduct the class next week, okay, because otherwise we'll run out of time, we'll not able to complete. So we'll be having classes as usual on the 5th. Okay, that's the first announcement. And the second thing is that because you have a week of holiday and also a test week, so this particular submission for this particular experiment, the submission deadline would be on 19th. So basically, you're going to get 3 weeks. Okay, so 19th is the third Tuesday of October. So okay, you're going to get 3 weeks for this. Okay, so these are the two announcements I had. So anything else you want to ask, or ask the TS about the experiment? Okay, or maybe the results, whatever you want to ask, you can ask.
Sir, can you please show the connections of the differentiator once, sir?
Yeah, you can show, but the instructions are already there. Huh? But anyways, yeah, you can explain.
Here the instruction means explain clearly, but again I will show, no problem. Delete all connections. I'm just performing again. Wait. Okay. Here we keep our V in to the capacitor input, and capacitor is connected to inverting terminal. This resistor is act as a feedback, so that's why V out to V in. There is a feedback, and this non-inverting terminal is connected to ground. Then here we are having this oscilloscope. So channel 1 is connected to V in directly, or it's connected to V in, and this output is channel 2 is connected to output terminal, so that we can see the input and output terminal simultaneously.
Yes, sir. Got it.
Okay.
Okay. Any other question? Any other question or clarification?
Sir, am I
Yes.
audible?
Yeah.
Sir, as the last week's as lab was deadline on 5th October, which is our exam week, will it be possible to extend it for 1 week so that we have the holidays and we can finish it up during the holidays? Because in between the exam, we have all the things to
See, you
study. There's no
already got 2 weeks, right? Anyways, like, see, the point is that number one is that during the holidays or on a holiday, we cannot set a deadline. Okay, so that's not allowed. Okay, so okay, maybe I will take
not
because
supposed
you're
to extend the
asking.
deadline. Those who want to submit
Yeah.
before they can before the holidays, but those who
We
want
cannot officially set a deadline. We cannot officially set a deadline on a holiday. Okay. Yeah. So what we can do is that especially which are like the weekdays which are declared holidays. Okay, we cannot set a deadline. Okay, Saturday is still fine. Saturday, Sunday is still fine. So what we can do is that maybe we can set a deadline on Sunday. Maybe because you are asking. Okay, that Sunday would be basically, so your deadline is 5th. So we can set it on 10th. We'll give you 5 days. But then the deadline and the end date will be the same date. Deadline and the end date will be the same date. Okay? Will that do?
Okay, sir.
Yes, sir, that would be great.
So that is
Yes, sir.
really helpful, sir.
Okay.
Because
Okay.
sir, there's no study
we'll
leave
set
for
on
us,
Sunday.
so we are in a hectic schedule.
Yeah, semesters are hectic, whether offline or online. It is always hectic. That is no doubt about that. Okay. So the TS, so you can upload this slides that you have just presented. Okay, and also set a deadline for this particular like op-amp experiment to be on the 19th of October. Okay, so these are the two instructions.
Yes, sir.
Anything else? Anyone wants to say anything else? Otherwise, we'll conclude. Okay then. So there is no question. There are no questions anymore. So bye bye then. Thank you.
Thank you, sir.
Thank you, sir.
Yeah, thanks. Bye.